My name is Veronika Miron, and on behalf of my co-authors Sebastian Lemmermann, Umut Çakmak, and Zoltan Major, I would like to present our paper Mechanical Characterization of 3D printed silicon elastomers. We are from the Johannes Kepler University, the Institute of Polymer Product Engineering in Linz, Austria, and the work was funded by the Land of Upper Austria as part of the project Medical Education in Surgical Aneurysm Clipping, short MEDUSA. Additive manufacturing, also known as 3D printing, is to build up a structure layer by layer. This allows more design freedom than conventional manufacturing techniques, allowing sometimes even the waste-free production of parts to create complicated freeform shapes, and even to produce topology-optimized parts with the reduction of material where unnecessary, inside the part and outside. With lattice structures, load paths can be optimized and structure mechanical properties selectively influenced. Silicone elastomers can be tailored to a broad range of mechanical properties and find application in damping, sealing, biomedicine, and mold making or prototyping. With 3D printing of silicone elastomers, we combine the advantages of the technology and the material. We built a customized two-component silicone printer with the printhead Viperhead 3.3 from the company Viscotec Pumpen- und Dosiertechnik GmbH from Germany. It has a large print area of 210 mm times 270 mm times 300 mm and a 750 watts printhead, print bed heating, automatic print bed measurement and leveling, and a pneumatic material feed. The silicone rubber's two components are dosed with a continuous piston system into a static mixer and extruded through a nozzle onto a heated build platform. After each layer, a 1000-watt halogen lamp is moved back and forward over the print bed with an adjustable waiting period between and initiates the material cross-linking through heat. Two materials were 3D printed. Silastic 3D is advertised for 3D printing applications, whereas Dragon Skin is a biocompatible silicone elastomer and commonly used for molding. For Silastic, a proven setting was chosen, while for Dragon Skin, 3 different print settings were compared regarding dimensional, visual, and mechanical properties. All specimens are printed with a 0.4 mm nozzle, a bed temperature of 70 degrees, and a layer height of 0.25 mm. The print speed and speed after heat source for Silastic and the first and second Dragon Skin setting was 10 mm per second, and was doubled to 20 mm per second for the third print setting of Dragon Skin. The waiting time of the heat source was 2 seconds for Silastic and Dragon Skin's first print setting, and was increased to 4 seconds for the Dragon Skin's second and third print setting. As commercially available material for 3D printing silicones, Silastic was printed and characterized using uniaxial tension as well as compression, biaxial tension, and pure shear tests. Additionally, Dragon Skin was tried for the printing process, and compression test cubes could be fabricated as well as tested. All tests were performed on a Bose test bench with an axial actuator and a 450 Newton load cell at room temperature. For each test type and speed, at least 3 specimens were fabricated and tested. Tensile test specimens with the ISO 527-5A geometry were punched out of a printed rectangular plate with 120 mm times 80 mm times 1 mm to avoid the influence of printed perimeters. The printed plate was filled fully with ±45 top-bottom layers. The specimens were tested and displacement controlled with 1 mm per second and 10 mm per second until the force limit of the load cell. For the biaxial tensile test, 2 mm thick or octagonal plates with an outer diameter of 140 mm were printed with full ±45-degree top-bottom layers, from which cross specimens with 35 mm broad arms and 20 mm radii were punched out to avoid the influence of perimeters as well. The tests were performed at 0.1 mm per second, 0.5 mm per second, and 1 mm per second, respectively. The pure shear specimens had the dimensions of 10 times 100 times 1 millimeter, with half cylinders of 10 millimeter diameter added on the long sides for clamping. The pure shear specimens were directly printed, fully filled with ±45-degree top-bottom layers, and tested at 1 millimeters and 10 per second and 10 millimeters per second. The compression tests were performed on cubes of 20 millimeters times 20 millimeters times 20 millimeters, printed with one top and one bottom layer and one perimeter. The cubes were filled with 100% rectilinear infill pattern. Additionally, 12 Silastic cubes were printed with 10% grid infill. These three loading and unloading cycles were performed up to 12 millimeter displacement for all but the 100% filled Silastic cubes, which were only tested up to 7.5 millimeter displacement due to the force limit of the load cell. The testing speeds were 0.1 millimeters per second and 1 millimeter per second for the compression and 1 millimeter per second for the unloading. To check the dependency of the print orientation, some specimens were also tested in X direction. To the results of the 3D printing. All 100% filled Silastic specimens could be printed with satisfactory quality. However, for the 10% grid infilled cubes, the 1 perimeter and low infill amount led to small holes in the walls, and the top layer was not closing due to insufficient support from the lower layers. This led to spread in the compression test results of these specimens. The dragon skin cubes were printed with 3 different print settings: an increase in heating time between layers, and further on doubling the print speed increased the dimensional and optical qualities. The sides for the first and second print settings with less heat influx and print speed than for the third print setting showed wavy sidewalls and holes inside the cube. Overall, the third print setting would be chosen to keep printing dragon skin parts. Overall, the results of the material characterization show nonlinear behavior that can be approximated with hyperelastic material models. The 100% module of the printed Silastic ranges between 2 to 2.5 megapascals, which is in accordance with the manufacturer's datasheet. In compression, both tested materials show hysteretic behavior. Testing the Silastic specimens at different strain rates showed no significant influence on the stiffness. This is in accordance to results found for PDMS and Ecoflex as presented in JACMAC 2021. The independency of Silastic and dragon skin silicone rubbers on the loading rate at ambient temperature can be of advantage for the prediction of the part behavior where the loading case is not fully known or where different loading rates are expected. The compression tests of the 10% filled Silastic specimens strongly indicate the influence of print quality on the stress-strain curve. The specimens that showed stop-and-go extrusion at their walls ended up with small holes in their walls. This results in consistently more compliant specimens due to open cell compression behavior where the air escapes cells compared to specimens with closed walls where the air is trapped in the cells and gives resistance to the load, which results in higher compressive loads at the same displacement. Buckling behavior is exhibited only by 10% filled specimens tested in Z direction with buckling strains between 5 to 25% and stresses between 0.01 and 0.22 megapascals, depending on the wall quality. Overall, Silastic specimens tested in X direction show higher stresses at 30% strain than specimens tested in Z direction. However, for the 100% filled dragon skin specimens, it is opposite, suggesting further investigation of the orientation dependency with more specimens would be necessary. The print settings changed the stiffness and strength at 50% strain for the dragon skin samples only marginally, so that the first print setting gives the highest strength with 0.34 megapascals, followed by the third print settings with 0.31 megapascals, and then followed by the second print setting with 0.28 megapascals. The average compressive strengths at 30% strain are 0.74 megapascals for 100% fields elastic, 0.13 megapascals for dragon skin, and 0.02 megapascals for 10% fields elastic. That makes the 100% fields elastic 37% stiffer than the 10% fields elastic, which shows the influence of the amount of infill for the compressive behavior of the part. Even though dragon skin is with the shore A hardness of 10 softer than elastic with shore A 50, the apparent hardness of a elastic part can still be lower than for the dragon skin part, as apparent hardness is a combined effect of the material's intrinsic hardness and its porosity. In our case, the 100% field shore A10 material shows 6.5 times the compressive strength of a 10% shore A50 material. As the haptic experience of a part is influenced by the mechanical thermal surface properties and purity of the material, the apparent hardness of a structure influences the user perception. This is relevant for the experience of anatomical models that should mimic the haptic properties of the human body to perform medical simulations, for example, for neurosurgery. With brain being the softest material in the human body, with an elastic modulus of 0.5 kilopascals up to 16 kilopascals, depending on the strain rates, the ability of adjusting the stiffness and apparent hardness of a brain model is very valuable, as otherwise only soft hydrogels would show this behavior, which however need special humid storage conditions. For fitting a hyperelastic material model, the experimental data were averaged over all loading rates. From the compression tests, only the results for the 100% field specimens were considered. The stress strain data were input into the software M calibration for the different loading types, and all available hyperelastic material models implemented in the CAE of software Abacus were fitted and evaluated for their reliability to describe the material behavior. Incompressibility was assumed for all fits. The best fits were then evaluated in Abacus and their stability limits were extracted. Satisfying fits for material models were achieved with the second and third degree octane models with R2 0.952, as well as the van der Waals model with an R value of 0.949. The material model parameters are given in this table and can be used as input in Abacus using the millimeters, newtons, seconds, and Kelvin unit system. While the van der Waals model is stable for all strains, the lower and upper strain limits for the octane models are given in the table below. In conclusion, we can say extrusion-based 3D printing of temperature-initiated cross-linking silicone rubber allows to create parts in a wide variety of apparent hardness. Apparent hardness is a combined effect of the material's intrinsic hardness and its porosity, thus reflecting the component hardness that reaches beyond the material hardness. The adjustability of the infill amount enables engineers to select the material normally applied only in a small sector for parts with specific hardness requirements, for example, elastic A with shore A50, and apply it over a broader range towards lower hardness, for example, down to shore 00. Utilizing lattice structures and load path optimization to desired structural compliance can be achieved. As design limitation, it should be kept in mind that the lower apparent hardness limit is reached when the infill structures are insufficient to carry the outer perimeters and top layers. For example, in our experience, to ensure that the top layers are closing with the elastic, the grid infill amount should not be lower than 15% at 0.25 millimeters layer height, printed with a 0.4 millimeters nozzle. By selectively extruding material where it's necessary to ensure structural integrity of the part, the advantage of 3D printing is owned also for saving material. Not only can the inner and outer topology of parts be optimized regarding the overall mechanical properties of parts, but minimizing the use of material allows to save resources. For engineering applications, this opens up the possibilities to use stiffer materials and create parts with lower infill density. to achieve the same overall part performance that otherwise would require a more compliant material. Further on, the independency of the mechanical properties of the strain rate at ambient temperature is useful to predict the reaction of the part for applications where the loading rates are unknown or range from low to higher loading rates. However, investigating if hysteretic loss due to intrinsic viscoelastic properties of silicone elastomers leads to cumulative temperature increase large enough to change the material response towards strain-dependent behavior could be interesting for further thermodynamic testing.